Okay, so in this video I'm going to find the definite integral of the function s squared minus 2x using right endpoints. So assuming you already know the definition of a Riemann sum, as an integral as a Riemann sum is this limit, is the limit when n goes to infinity of a sum of I equals 1 up to n of f at some test points xi star in general, but when you use the right endpoints, so that would be xi times the delta x. So that's the definition of our Riemann sum definite integral. Now I'm going to do this in two steps, and I'm going to forget about the limit for a minute. So I'm going to keep this limit and leave it there to the end, and I'm going to deal with this part for most of this writing, and then at the end take the limit. It's just a little bit of less writing that way. So I'm going to deal with this sum here. Okay, now we need to remember who is the delta x. So the delta x is the width of my rectangle, and the width of the base of the rectangle. So delta x is going to be b minus a divided by n. In this case, the b minus the b and the a are these values, the integral that you're taking the integral from. So it's just 2 minus 1 divided by n, so really it's just 1 over n. And the xi, in general, it's the a, it's the right end point, so it's the a plus I times delta x. So it'll just be a plus I over n. So if you remember what this is happening, we're taking the integral, finding the area of a sum here between a and b. We're cutting this into tiny pieces, taking smaller later, and this is my x1, for example. This is my x2. So this distance is my delta x, right? So if I'm splitting b minus a in n pieces, that's what this delta x is, right? And then my xi is a, so this value, plus I times my delta x. So that my x1 would be a plus 1 times this distance, and x2 would be a plus 2 times that distance, and so on. So that's where this comes from. Okay. Now in this case a is 0, so it's very simple. So in this case a is 0, so it makes it's just I over n. Okay, so in this case my xi is just I over n because my a is 0. Okay, so let's go for this. So then that means that I need to find this sum from I equals 1 to n of, I'm plugging in into this function f. Whenever I see an x, I'm doing xi, right? So it's going to be xi squared minus 2xi. But I is just, xi is just I over n. So this is going to become, sorry, I was totally wrong. My a is not 0, my a is 1. So my xi is 1 plus I over n. So when I plug it in here, I'm going to get my xi, let me write it if you want, xi squared minus 2xi, then times the delta x. But this is going to become I equals 1 up to n. It's going to become 1 plus I over n quantity squared, that's for this term, and then minus 2 times 1 plus I over n, that's for this term. And all that is still multiplied by the delta x. So maybe I should probably keep track of that delta x in a different color, like that. So that delta x is this one that was here. Let's change it to green. Okay, so now, oh sorry, and then that delta x, since I'm plugging it in, why don't we just tell you it's 1 over n, right? Okay, so now we have a lot of things going on here in this sum. It's one finite sum, and then I have some constants multiplying. So notice that what changing with the sum is the I. So this is the variable changing inside the sum, and it shows up here and it shows up here. The n is really a constant, right? So the n is the upper bound of how many terms you're adding. So the n is a constant, so I can deal with I have these formulas here where the n is, I'm dealing with this constant here, and you can bring it inside or outside of the sum. So dealing with that 1 over n in that way, sorry, my colors didn't match, but dealing that 1 over n can be brought in front, and then I can have this sum. And now I'm going to expand this one, so it's 1 plus 2i over n plus I squared over n squared, correct? And then I have another sum over here. So I'm going to do minus 2 and minus 2i over n. So this turns out to be something like that. The 1 over n was brought in front. Okay. Now something nice here is that these two terms cancel. So the 2i over n and the 2i over n show positive or negative, so they cancel, they're not 0. And if I combine the 1 with the negative 2, it's just a negative 1. So this simplifies a little bit. It's going to be 1 over n times a sum when I equals 1 up to n of, I really just have I squared over n squared, and then I have minus 1. Okay. And now we can break this one up. I'm going to do it, I'm going to have two terms inside the sum, and I'm going to bring it up, I'm going to use this one. I'm going to combine that one and this one because in the second one it's a constant. But the first thing I'm going to do is separate this as 2. So I have 1 over n. Oh, I started making it green, but let me go back to make it green. It's not that important now. That's a lot simpler now, what I'm doing. I'm going to have the I squared over n squared. Now look at something here. I'm going to write it like this. 1 over n squared times I squared. Why? Because if I do it like that, then this term here is a constant. Again, remember, this is a sum over the i's. So this 1 over n squared can really be brought outside of this term, and I'm going to do it in this stage. So this is a constant for this sense, and I can bring it outside here. Okay, so if I bring it outside, it's going to be 1 over n cubed. I can't do that automatically, so I'm going to change this term now and make it 1 over n cubed. And since it's not really the 1 over n, I'm going to put 1 over n cubed outside. Okay. And then I'm going to have here the sum of the I squares. Okay. And then on this side, on the right, I'm going to have negative 1 over n, so minus 1 over n, still times the sum when I equals 1 up to n of 1. Okay. Okay. So I'm having the sum of the I squares and then the sum of 1s. Now, if we have these formulas, I'm going to have to use this formula for sum of I squares. And the sum of 1s is really just this one. When c is a 1, I'm doing n times a 1, right? Just adding 1 plus 1 plus 1 n times. So this one is easy. That's just an n. For the other one, we need to do something. So I'm going to cheat here and shrink this to have more space. Put this on the side right there. Okay, and now let's start writing over here. So what I have was the sum became 1 over n cubed of the sum of I squared, which if I remember correctly was, let's look it back, it's n times n plus 1. So it's n times n plus 1 times 2n plus 1 divided by 6. So that's what this term is. And the other one was just, we said that this is n 1 plus 1 plus 1 n times, so it's an n. So I'm going to put an n over n. Okay, so if we expand this term, this becomes n 2n squared and n, so I get to 2n cubed. I get 3n, I believe, 3n, so times n, 3n squared. And I get 1n squared, plus 1, sorry, plus 1n, plus n. So now this is divided by 6n cubed. And this is minus 1. Okay, so this is the as much as I can simplify this sum, okay? But remember that I didn't do this. I didn't take this Riemann sum. I still need to take this limit. So now to complete this problem, I need to find the limit when n goes to infinity of this thing that I have here. Then if you have to remember what these limits, how to find these limits of these guys from Calc 1, if they have the same power in the top and it's a rational function with the same power, then it becomes just the leading coefficients, right? So just a 2/6, which is a 1/3. So this is 1/3. And then it's minus 1, so it's negative 2/3. Okay, so that's how you can deal with these problems. They look like it's overwhelming to do this. I didn't take the limit until the very end, right? So this limit, I left it for a side, and at the very end I took it, once you have this expression. Okay.